So I'd like to go back to this chapter. Remember, is both frictional force and uniform circular motion. Oh, and by the way, we are not going to go into the details of air resistance. That part of the chapter we're not going to go into details of. All the friction we're going to do is the friction we've already done. We'll do a few more examples, maybe in video lectures, certainly in class. We'll do a couple more examples, homework, but we're not going to do air resistance section. But I'd like to go back to uniform circular motion. We had talked a little bit about uniform circular motion, but we can do a few more problems there too. Okay, we're back for our next exciting problem. And that's going to be a circular motion problem that somebody in class had asked about. It was a good question, and it's a good problem to solve. So let's go ahead and talk about what does the Earth's rotation do to us. So this is actually something relevant to you, super important. Like, what would happen if the Earth rotated? Would I fly off into outer space, or would I somehow go slamming into the ground or something like that? No. Don't worry about it. If the Earth stops rotating, we wouldn't even notice. Well, maybe the tides, maybe the water would slosh around a little bit or something, and, we'd get a little wet. But we'd stop getting tides. But, yeah, otherwise, not much would happen. Moon wouldn't fall to Earth. We wouldn't all die. Okay, so let's talk about what would happen if the Earth stopped rotating. So, let's see. Purple. Okay. So here's the thing. Here's the Earth. It doesn't look much like an Earth. That could have been just a smiley face. But here's the Earth, right? You got some land mass up there, some land mass up there, some big land masses over here, depending on if we're being U.S. centric. And here's actually Europe, maybe here, and I don't know. Okay, so there's a great picture of the globe. Okay, so I put the U.S. right at the equator. That probably wasn't a good idea. Although, it's getting warmer, so it doesn't mean we're moving closer to the equator, it just means climate change. But, okay, so let's call this the equator. And let's just ask what the effect of being at the equator is. So let's say that you're standing here at the equator. Here you are a giant standing here at the equator, and ask what's the effect of you. I guess you're somewhere maybe you're in Russia, Eastern Europe somewhere. Okay, and no, Eastern Europe would be a bit too far north, but anyway, maybe you're probably more likely in the middle of the ocean. Okay, so you're standing there at the equator and ask, what's the effect of the Earth's rotation on you? So let's just draw a free body diagram of you. So really the question we're trying to ask is, let me make this pen a little smaller. What is the effect of Earth's rotation on you, or me, or a bear, or a fish swimming at the equator? Okay, so let's go ahead and draw a free body diagram of you. We'll give you a smile. And let's now, rather than keeping the orientation of the Earth as drawn, let's keep your orientation and say that, well, okay. So I'm actually flipping the whole thing 90 degrees here, right? And saying that the force due to gravity is down, Fg. In the other picture, force due to gravity would be in that direction. Okay, so I'm flipping it 90 degrees. Force due to gravity is down. Force due to the fact that you're standing on the water. That makes you pretty important. Standing on a platform on the water gives you a normal force in the upward direction. And are there any other forces on you? Well, if you really think hard, you realize in order for you to be stuck to the Earth and moving with the Earth, there's got to be a frictional force. But let's ignore friction, but just assume that you are moving with the Earth's rotation. In which case, there's no ropes attached to you, no springs attached to you, no friction, and actually all the forces are drawn here. Okay, so this is a correct free body diagram. So then we want to choose a positive direction. Positive direction, if we're being careful, is going to be the direction of acceleration of you. Are you accelerating? Are you accelerating? And the answer is yes, indeed, you are accelerating, because you're on this Earth that's rotating in a circle, so you must be accelerating towards the center of that circle. And yes, it's gravity that is making you accelerate towards the center of that circle, because only gravity is pointing towards the center of that circle, right? Look at the picture of you standing on the globe. Gravity is the only force pointing in that direction. It's what's making you go around with the Earth. So the acceleration is in that direction. So we're going to call that the plus x direction. And we're going to write down Newton's second law, F net equals ma. And in the x direction, F net x equals max. I know it's a little redundant, but that's okay. And fill in the net force in the x direction. If plus x is down, then it's going to be plus Fg, your weight, minus Fn equals ma. Now, what do I put on the right-hand side? On the right-hand side, I put my mass, and what's my acceleration? What's my acceleration? Okay, so now I hear all of you saying g, g, g. No, my acceleration is not g. I'm not falling I'm not in free fall. Keep in mind that my weight is mg, but my acceleration, if I'm sitting flat on the ground and the ground is not moving, my acceleration is not g, it's 0. In this case, the ground is actually rotating underneath me, and my acceleration is the acceleration due to the circular motion of the Earth. It's like, make this an amusement park ride. Put me on a merry-go-round, right? And my acceleration would be the acceleration of the merry-go-round going in a circle. That's what's going on here. No, my acceleration is not g. My acceleration would only be g if I was in free fall, if I was falling, with the only force on me being g, but being the force of gravity. But I'm not. So I'm on the Earth that's rotating. So the acceleration that goes here, it's still an a, but this a is the acceleration due to the rotation of the Earth. Oh, but wait, it's a rotation problem, so we always replace acceleration with mv squared over r. I'm sorry, acceleration with v squared over r. So it's Fg minus Fn equals mv squared over r. So this is what Newton's second law tells us. Okay, so if the Earth wasn't rotating, what would that tell us? If the Earth is not rotating, if Earth stops rotation, that means that v equals 0. If the Earth stops rotation, that simply says that Fg minus Fn equals 0. What does that tell us? Does that tell us that we are weightless? Does that tell us we're being thrown off the Earth? No, what that tells us is that the gravitational force on us is equal to the normal force, which is no different than any other time we were standing on the ground. We said the gravitational force is equal to the normal force. So actually, when we have an object flat on a surface and we say that the gravitational force is equal to the normal force if there's no other forces acting on it, that situation is where we're assuming the Earth is not rotating. So up until now, we've always assumed the Earth is not rotating, and we'll keep assuming the Earth is not rotating. But for the sake of this problem, let's include the rotation of the Earth. So what does the rotation of the Earth do? So back to our original question, what is the effect of the Earth's rotation? The effect of the Earth's rotation is that it effectively changes our weight, right? Because this equation is no longer true. And remember, the weight that we feel, we don't actually feel Fg, we feel Fn. When we weigh ourselves, we put ourselves on a scale that's on a surface. We stand on a scale that is on a surface, and that surface, the legs went in the wrong direction. And that surface is on Earth. And Fg is equal to Fn, right? Fn is how hard the scale is pushing back on you, and that, by Newton's third law, is how hard you are pushing on the scale, and that's what the scale reads. Fn is what the scale reads. The scale does not read Fg, it reads Fn. If the acceleration of the Earth is 0, then the scale reads Fg, right? If the acceleration of the Earth is not 0, if the Earth is moving, so the velocity is not 0, so the acceleration is not 0, therefore we have to go back and say Fg minus Fn equals mv squared over r. And therefore that tells us that Fn equals, solving for Fn, equals Fg minus mv squared over r. So without plugging in any numbers, right, Fn is how heavy we feel. That's our effective weight. We've talked about this in class. It's what a scale would read. So without plugging in any numbers, what I've just shown you is that the rotation of the Earth means that we feel lighter than we are. lighter by this amount, right? The actual weight is Fg. The weight by a scale at the equator is going to be Fg minus mv squared over r. And that's at the equator. If we're not at the equator, these values will change. But that's at the equator. And so then we can say, okay, so what's the difference between Fn and Fg? How much lighter do we feel? Is this effective? Are we really a lot heavier than we think we are? And the answer is no. mv squared over r is not a big value for the Earth, right? So let's go ahead and calculate that. Okay, so if we want to solve this question about how much heavier are we than we actually feel, and I'm saying, again, doing this at the equator, then to plug in these numbers, we got to say what is the speed of the Earth's rotation at the equator, and what is the radius of the Earth at the equator. If you want to find out what it is in Lynchburg, Virginia, the radius and the speed of rotation are going to be different. And so you can figure out what it is there. Because remember that the Earth rotates about an axis. So the radius at the equator is this right here. The radius at Lynchburg, Virginia is this right here, right? It's something smaller. And so the speed must be different too, because we go around a smaller circle in the same amount of time. We're moving faster in Lynchburg, Virginia than we are at the equator. So if you're curious about that, you can calculate that, but I'm just going to do it at the equator. So I'm going to write down some numbers. Actually, before I pause and write down some numbers, remember that the speed of something moving in a circle, people keep on asking me this question. The speed of something moving in a circle, if it's moving in uniform circular motion at constant speed, that means uniform circular motion, all we have to do is figure out how far it moves in a circle, the circumference, 2 pi r, and how long it takes to move around that circle over a period. So every time we solve for speed for a uniform circular motion problem, it's always 2 pi r over t, okay? Okay, so I'm going to go ahead and plug some numbers in. So I just looked up and calculated some numbers. We get the radius of the Earth at the equator is 6.37 times 10 to the 6 meters. The period of rotation, we go once around every 24 hours. That's 86,400 seconds. And so now it's just a plug in. So let's say if your mass is 60 kilograms, then your weight, Fg, is equal to mg, which equals 60 times 9.8, which is about 600 newtons, right? So your weight is about 60 times 10 meters per second squared is 600 newtons. And then we can compare that to mv squared over r. mv squared over r term is equal to 60 kilograms times, now I'm going to go offline. So if I go ahead and plug in the radius of the Earth and the period of rotation of the Earth to mv squared over r, what we get is 0.32 newtons. 0.32 newtons. Let's go back to this equation. Remember, Fn equals Fg minus mv squared over r for this particular situation. Fn minus Fg equals mv squared over r. So if Fg is 600 newtons, Fn is equal to, I could do the math, Fg minus mv squared over r. So if Fg is 600 newtons, mv squared over r is 0.32 newtons. Therefore, the effective weight is smaller by such a small amount, right? We don't really notice the difference. I mean, it's a measurable difference, right? Then the normal force that the floor exerts on me is slightly smaller than my actual weight. And it's smaller by that amount than my actual weight. So the fact that the Earth's rotating, the difference is that it makes us feel a tiny bit lighter than we actually are, but not really noticeable. So I guess that's it. We'll call that a day. And we'll solve a couple more, maybe one more friction problem, one more rotation problem, maybe a friction problem with rotation in class on Friday, and then probably take us through a little bit of Monday, and we'll start the new chapter, the important chapter being energy. I don't know how to spell energy. Energy. There we go.